Okay, good morning. I'm going to talk today about the estimation of dynamic discrete choice games. There are many economic phenomena where it's important to understand how economic agents make decisions that are dynamic and have spillover effects. By dynamic, as you know, we mean that these decisions have implications not only on today's outcomes, but in future outcomes. And by having spillover effects, what we mean is that this decision can have effect on outcomes or payoffs, not only of their own agent, but of other agents in the economy. The typical tools that we use to study dynamic phenomena is dynamic programming. And the typical tools that we use in economics to study economic phenomena that imply spillover effects across agents are games. And then dynamic games, basically, we are putting together these two type of tools, okay? Then I'm going, perhaps a very common type of example, and the one that I'm going to use as an example here in today's lecture is dynamic games of oligopoly competition. We have an industry with a few firms operating in that industry. And of course, these firms can compete in prices and in other more static decisions. But they also make investment decisions that have implications about future profits. And these decisions, of course, they have implications not only on the profits of their own firm, also on the profits of competitors, okay? Then I will start with some basic features about the structure of these type of models. I will introduce the concept of Markov perfect equilibrium that has been the most commonly used concept in the empirical applications of these models. I will introduce incomplete information in these models, and you will see why. It's somehow a trick to incorporate unobservables that have a very simple structure, or they are very easy to deal with. I will also comment that typically in most applications, we should incorporate not only this incomplete information and observables, but other type of common knowledge and observables. And then I will talk about different type of estimators. Here I say sequential estimation, but I will start with maximum likelihood estimation. How will maximum likelihood estimation will work here, and why is challenging in many applications. And that is going to motivate simpler type of approaches that I describe as sequential approaches. I will start with two-step estimation. Two-step estimation, CCP estimation in these applications will have also very substantial limitation because the large measurement error in the estimation of the choice probabilities. And that motivates other type of sequential estimation that are full solution methods, but full solution methods that are substantially simpler to implement than maximum likelihood nested fixed point out. Okay. Okay, then let's start with the structure of this class of models. Time is discrete and indexed by t, as in most previous lectures. And we have n, okay, we have n firms or n players, okay? I will be using players and firms both as the agents in this type of models that we index by I. Every period t, each player makes an investment decision. I'm going to use a variable a to represent the investment decision of this agent, and they make these investment decisions to maximize the expected and discounted intertemporal payoffs. Then delta I is the discount factor of player I, and pi is the payoff function of player I at period t. Okay. In my lecture, I will focus on discrete choice dynamic games. That is, A belongs to a finite and discrete set of possible choices. Okay. Tan will talk later about dynamic games where the action is continuous. Okay, then let me talk about, I have mentioned decisions. Let's talk about the states, payoffs, and transitions, basically the primitives of this model. We have that the current payoff depends on the own action of the player, but because we have a game, it depends also on the actions of the other players in the game. I'm going to use A minus I to represent the actions of all the players who are not player I. And there is a vector of state variables, X, that enters also in the payoff of player I. It's going to be relevant to distinguish between endogenous state variables that I'm going to represent as K, and there is a typo here, exogenous state variables that I will represent as Z, okay? Then the endogenous, as usual, the endogenous state variables follow transition or evolve over time, depending on the decisions of the investment decision of the player, while the exogenous state variables evolve over time independently of the decisions of the player. Okay. I'm going to put, unless I need to distinguish between the transition of the endogenous and the exogenous state variables, I'm going to put both together in the vector X. And what we have is that these state variables follow a control Markov process with this first order Markov transition probability. Okay? Or you can see that this vector evolves depending on the actions of all the players. If I do not have use a sub-index I for the action A, that means that we have the vector of the actions of all the players. Okay? An example that we can keep in mind during this lecture is competition between firms in a differentiated product industry, where firms compete in prices, but they also compete in quality. And quality requires some investment decisions which are irreversible, okay? Involves some cost investments in quality. Then we can represent we have N, capital N, differentiated products in the industry, and firms make every period T two type of decisions: an investment decision in quality and a pricing decision. Okay. Then the vector of state variables in this model consists. Then I'm representing the quality of the product I using K subindex IT. And the vector set represents any other exogenous variables that, for instance, market size, consumer demographics that evolve exogenously in this market. The exogenous variables and the endogenous variables, of course, the quality of the product is different. We have a vector of quality, it's one for each product. And the vector of exogenous variables may be common across all the firms or may vary also across all the firms. And then we will have a vector of exogenous state variables, one for each. Okay. Then every period T, firms know the quality of the different products. They know the exogenous state variables. Then they know what is the demand for the product. They know their marginal cost and competing prices à l'arbitrage. Okay. And this is a very common structure in this type of dynamic games. There is an static competition that can be Cournot, can be Bertrand, okay? But it's static, okay? We could consider in a more complicated model where price competition is also dynamic. But here we can think in a model of price competition that is static. This is the framework that is called the Ericsson-Peickes type of framework in dynamic games of oligopoly competition. The pricing competition is static, but then there is an investment decision in quality, in capacity. Okay? Then this price competition, every period T, will determine a Bertrand equilibrium. equilibrium prices, equilibrium market shares, and that determines the revenue and the variable profit of firm I at period t. Now let me use this RIXT to represent the indirect equilibrium Bertrand profits of firm I at period t, okay? Given the qualities that the firms have and the equilibrium prices, these are the equilibrium profit that a firm will receive in the market, okay? If this firm has higher quality, then its price could be larger, and equilibrium profit for this firm will be large. And that's incorporated in this equilibrium profit function. But this is an static equilibrium profit function, okay? And then we have the total profit, that is just this variable profit minus the cost of investing in quality. Every period t, the firms decide, do I want to make an investment to improve the quality of my product? Do I want to make a disinvestment to reduce the quality of my product? Or I keep the same quality as in previous period, okay? Okay, and then we will have a model for the evolution of the quality of the product, okay? It could be deterministic, as in this way. In this case, A, you can think that A, the set of possible choices could be either positive or negative. You can, in principle, increase or reduce quality, okay? Okay, then in terms of the transition of the state variables, we could consider a generalization of this very simple transition rule, okay? We could consider different versions of transition rules. For instance, in a model of market entry and exit, what is the endogenous state variable? The endogenous state variable is which were the firms that were in the market at previous period, okay? Because those are the firms that are competing today in prices, for instance, okay? The only thing that you have to decide is whether you are in the market or you are not in the market, okay? And this basically, in this case, this determines the firm. If this is equals to 1, that means that this firm is an incumbent firm that is active in the market at period t and will be competing in prices at period t, okay? Then the evolution of this endogenous state variable is trivial. Next period state variable is just today's decision of being in the market, okay? You can see that in the timing that I'm considering, there is a time to bill assumption. I'm considering a version of the model where it takes one period to be active in the market. You decide to be in the market, you make the decision today, but you will not be really active and competing in prices in the market until next period, okay? We could consider other versions of this transition rule, where basically, like in the previous example, quality is quality at previous period, quality at next period is today's quality plus the investments in quality. We could incorporate depreciation, deterministic depreciation, or we could incorporate also some stochastic depreciation. And of course, you could consider more general versions of this transition property, okay? I'm going to represent the evolution of the state variables, as I mentioned before, using this transition rule, okay? Okay, then this is the primitives of the model: payoffs, transition, or evolution of the state variables, and preference. Okay, then what is the equilibrium concept that we consider? Let me start considering a very general equilibrium concept that is basically Nash equilibrium, a very general version of Nash equilibrium for dynamic games, okay? Then let's consider the information set. Suppose that the information set of players at period t consists of all the history of previous states and previous decisions from some initial period until period t, okay? That's what I represent by calligraphic I subindex T. It's the history of all the outcomes in the past, decisions and states, okay? As long as you want, okay? And suppose that players, okay, players' strategies are functions of this information, okay? Given the information at period T, I'm going to form a decision, a strategy that depends on my information at period T, okay? Then suppose that player I believes that the rest of the players, okay, are going to behave now and in the future according to some strategy, some particular strategy function. This is the vector of the strategy functions of all the players who are not player I, okay? Then if a player takes as given the strategies of the other players, now we can construct what we could call an indirect payoff function and an indirect transition probability. What is exactly what I mean by an indirect payoff function? Well, there are payoff functions and transition probabilities where now player I takes as given the strategies of the other players, and now then this payoff and this transition probability depends only on the action of player I, okay? Basically, the payoff of player I at period T depends on his own action, on the actions of the other players, and the state values. But here, because this player believes that the other firms will behave according to this strategy, and this should be calligraphic IT, this is a typo here, then we will have a payoff function that again depends on the action at period T and calligraphic IT, okay? Similarly, we can consider, we have that the transition probabilities of the state variables depends in these actions of the other firms at period T. We can replace the actions of the other players by the corresponding strategies. And then we have the transition probability that depends on the whole information at period T. And this basically, because the information at period T plus 1 is just the information at period T and X at period T plus 1 and the actions at period T, then we can basically, these transition probabilities for the states imply a transition probability for the information set, okay? Okay, then let's take these payoffs and these transition probabilities, and now we can define a single agent dynamic programming problem, okay? Well, basically, you can see that the payoffs and the transition probabilities now only depends on the action of player I. And taking as given how the other players will behave today as in the future, what I have as a player is just a single agent dynamic programming problem, okay? What is the action that will maximize my value, my intertemporal value, okay? And we can represent this as a Bellman equation, okay? The value of player I at period T depends on the information at period T, depends on the actions of the other players. That's why I'm indexing this value function with the strategies of the other players. And it's just the solution of this Bellman equation, okay? Where we have payoffs and transition probabilities that are indexed by the actions or the strategies of the other players. If we change the strategies of the other players, this Bellman equation and this dynamic programming problem will change. And of course, we will have a different best response, okay? Then the solution of this single agent dynamic programming problem is the best response of player I to the belief that player I has about which are the strategies of the other player, okay? Then we are in a very standard game setting, okay? We have players' strategies, which are functions in this case, and best response functions, which are well-defined best response functions, which are the solution of single agent dynamic programming. And then we can define in this setting an as equilibrium as an n-tuple of a strategy function, one for each player, such that everybody is best responding to the strategies of the other players. As simple as that, okay? Okay. Please. Well, okay, good, excellent question. I think I have been explicit somewhere, but I didn't mention. I'm considering infinite horizon. We could generalize this to finite horizon, and then these strategy functions will vary over time. Then each player will have a sequence of a strategy function from period 1 up to capital T. And then the best response, a player strategy will be all these functions. And the best response will be a best response in terms of all these functions for every period. Okay? I'm going to avoid that, basically, to avoid that more complicated notation. I'm assuming a stationary context, which is very common in applications in I/O, where basically firms can live forever and we have infinite horizons. Then in that case, the solution of the dynamic programming problem has an optimal decision rule that is time invariant, okay? And that's what we don't have a time in this. Of course, the behavior of the firm is different at different periods, but just because the state spaces, the state variables is changing over time. But the function, the strategy function is time invariant. It definitely has implications. It has an implications of they are not, we are capturing all, according to our model, we are capturing all the variables. Our specification of the state variables includes all the variables that can have an effect on the changes in the behavior of the firms or the players over time. Of course, you can include in X any type of aggregated state variables that you want, okay? And that, in that sense, at the end, I think that the empirical content of the infinite horizon and the stationarity is quite limited, okay? Because you can incorporate as many state variables that vary over time and that are aggregate as you want. Okay. Okay. Then this is a standard Nash equilibrium. Nothing about Markov perfect equilibrium yet. Okay. As you can see, okay, the state space in this setting is homogeneous. Okay, includes the whole history of states and decisions, okay? And it can be very large, okay? Then a common restriction in empirical applications of dynamic games based on the theoretical work of Maskin and Tirol and then the empirical framework of Erickson and Peikes is to consider that we are going to restrict to a particular type of subgame perfect equilibrium that is called the Markov perfect equilibrium, okay? And what is the key restriction in the Markov perfect equilibrium? The key restriction in the Markov perfect equilibrium is this one, okay? Is that the strategy functions that firms pay are functions only of payoff relevant state variables. That is, state variables that have an effect on today's profit or on expected values of future profit. Everything that is part of the information set, but that does not have an effect on today's or future expected profit is not information that the firms use to construct strategies. Okay, that's the key restriction of the Markov perfect equilibrium. Okay, what is the theoretical rationale for that provided by Maskin and Tirol? Well, the rationale for using Markov perfect equilibrium, why is this is an attractive restriction, okay, is that if we think in a meta game, okay, where firms or players could decide first how much information I'm going to use to construct my strategy. And after you have decided how much information, basically you first choose how much of this information set I'm going to use to construct my strategy. And then once we make this decision, they construct their responses and they play this game, okay? And in that type of meta game, okay, if a player knows that the rest of the players are using strategies that depend only on payoff relevant, there is no any game of conditioning your behavior on more information on variables that are not payoff relevant, okay? And there is not any incentive from deviating from this choice of your information if the rest of the players do not use more information, okay? That is not the case if you use less information. That is, if the other players are using less information than the payoff relevant state variables, there are gains of using information about payoff relevant state variables, of using more information, okay? And in some sense, you can see that the Markov perfect equilibrium is like an equilibrium of this meta game where we endogenize how much information agents use to construct strategies, okay? Okay. Of course, this does not come without restriction. As you can imagine, if firms can condition on previous histories of the decisions, it's going to be easier for them to coordinate some kind of actions, okay? We are going to have collusion probably is going to be more likely. It's not that we cannot have collusive outcomes using the Markov perfect equilibrium concept. We can, definitely. But extending the Markov perfect equilibrium concept to strategies that depends on previous histories of actions is going to make coordination and collusion in particular easier, okay? There will be more equilibria where we have this type of coordination, okay? Then the main motivation is practicality, okay? Is the dimensionality. We are reducing very much the dimension of the state space, okay? And that is going to be practical for empirical analysis, okay? You will see later that we can go even farther in this context, and that is going to take us to the so-called moment-based equilibrium. In the moment-based equilibrium, we are going to consider that firms play strategies that reduce the space of the state variables. Okay, that basically type of assumption will be motivated purely from reducing the dimensionality of the state space, okay? Okay, then a Markov perfect equilibrium is a n-tuple of strategy functions, time invariant because we are in a stationary framework where every player is best responding to the strategies of the other players, okay? Then we steal this type of best responding condition, but now these strategy functions depend only on payoff relevance. Okay? Okay, then these are the Bellman equation that defines the best response of each firm. Okay, but now, okay, this indirect payoff function is the payoff function of a firm when this firm is taken as given the actions of the other players according to the strategies of the other players. And similarly, the transition probabilities of the state variables now depends only on the action of player I because it's taking these strategies of the other players as given, okay? And it's best responding to this strategy. And this defines a single agent standard dynamic programming, okay? Okay, then questions about this? Okay. Let me go to the moment-based equilibrium, okay? Then there are many empirical applications where we have a relatively large number players, okay? And these players are not symmetric. They are heterogeneous in their payoffs and in their endogenous and perhaps exogenous state variables as well, okay? Then the dimension of the state space increases exponentially with the number of players, okay? If each of these state variables has x1 has support of k possible values, the number of possible values of the vector x, okay, will be k to the power n, okay? And this can increases very rapidly with the number of players, okay? And if each of the x variables, exogenous and endogenous, take 100 values, okay, and we have 10 players, then 100 to the power 10 is 1 million, okay, approximately. Okay. Then okay, this is no, it's much more than okay, it's 10 to the power 20, okay. Then that can make things quite complicated in terms of solution and estimation of this type of model. Then in that context, some authors have used the concept of moment-based equilibrium, which is basically an additional restriction, is a restriction on the set of possible strategies that firms play. Basically, the assumption is that when constructing their best responses, players, they consider their own state variables, okay? And then some moments, broadly speaking, some aggregation of the state variables of all the players in the okay? And suppose in the simplest example, a model of market entry and exit, the endogenous state variable is whether the firm was in the market at previous period or not. Here we will have the incumbency status of the other firms in the market. A very simple version of the moment base is that only matters how many other firms were in the market at previous period, okay? And I'm going to best response to that. And of course, that will be, in fact, Markov perfect equilibrium if we had a model, okay, where all the firms are homogeneous in their Fayot function. Because under that type of model, we will have that really the optimal strategies. The only thing that matters is how many other firms were in the market at previous period, because all of them, they have the same probability of market entry and the same transition. But if we have a game where agents are heterogeneous, okay, this becomes a restriction, okay? Assuming that when firms construct their base their strategies, they are going to consider only how many firms were in the market at previous period. That means that they are ignoring that some firms have higher probability of entry than others, okay? And under Markov perfect equilibrium, that will be taken into account, and then the moment-based equilibrium, that will not be taken into account, okay? Then it's a behavioral assumption. It's restricting our strategy, okay? Okay, but it can be very convenient because it's an equilibrium concept. We will take into account, we will endogenize players' actions, and we will be able to construct counterfactual experiments using our estimated model. But the computation of this equilibrium will be much simpler computation. Okay. Okay. Let me go back to the previous slide. Okay. Then so far you can see that I have not incorporated, I have not distinguished, we have a theoretical model where I have not distinguished between what is observable to the researcher and what is unobservable to the researcher. I have only X and X principle. I'm not distinguishing between observables and unobservables, okay? Then we could consider a standard extension of RAS dynamic programming problem for single agents to the dynamic game, okay? And say, okay, now let's suppose that XIT includes two different types of variables from the point of view of the researcher. the state variables that are observable to us, and the state variables that are unobservable to us, okay? Let's call them epsilon, okay? But suppose that we consider that these state variables that are non-observable to us, but observable to the players, are common knowledge for all the players, okay? The epsilon of firm 1 is known by all the firms. The epsilon of firm 2 is known by all the firms, okay? Well, that common knowledge assumption about the state variables is going to generate substantial problems in the econometrics of this type of models, okay? Basically, in the type of models that you have seen throughout the course, we have always a single crossing condition in terms of the unobserved. At the end, the decision of being in the market, of investing, of taking different actions, has a form that this epsilon is lower than something that depends on the unobservable. Of this difference between the epsilons of alternative 1 and alternative 2 is lower or equal than some function of the observable, okay? Once we consider epsilons in the context of games that are common knowledge to the firms, but they affect differently to the different firms, we have that we no longer have a characterization of the best responses where we have this single crossing condition, okay? And that is the case both in static and in dynamic, okay? Then that can complicate substantially the econometrics of this. And that's why I would say that universally, all the empirical applications so far of dynamic games, dynamic discrete choice games, have considered that the unobservables have private information, okay? That is the main reason, okay? There is other reason that is more technical, and is that a paper by Doroselsky and Satterwhite in RAN in 2010 showed that if we have only state variables that are common knowledge, okay, the XT that I have presented before, these games is very easy to get example. It's very common. This is not a rarity. It's quite common to have examples, okay, where the model does not have an equilibrium, okay? And then what they propose also in that paper is they saw that a very simple way of getting equilibrium existence for this type of models is to allow for some incomplete information in the payoff of it, okay? To allow for some variables that are known to the firms, okay, or by a firm, but not by the competitor, okay? Some private information type of values, okay? Then by incorporating this, in fact, independent private values or independent private information state variables, we can, and you will see that it's very easy to show that these models have an equilibrium, okay? And in fact, they might have multiple equilibrium, okay? Then introducing private information is a way of basically guaranteeing that these models have an equilibrium, okay? And at the same time, it's going to be a very convenient type of unobservable variables from the point of view of the research, okay? Okay, then let me extend this framework to incorporate private information, okay? And now we distinguish two different types of state variables. I will continue using XT to represent the state variables that are common knowledge to all the firms. These variables in the vector X, they are known to all the players at period T, okay? But in addition, we have that in the investment cost of firm I, we have a private information variable. Let's call it epsilon IT. Or it can be a vector of private information variables, one for each action, as we have seen in single agent models, okay? Then importantly, these private information variables are assumed independently and identically distributed over time, but also across firms, Okay, they are independent across. Okay? Then under Markov perfect equilibrium, now the strategy function of player I is going to be a function of its own pair of relevant state variables. And which are now the pair of relevant state variables for firm I, the common knowledge variables, and this private information. Okay. Of course, the private information of the other variables could not be in the strategy function of firm I because this firm doesn't know the epsilons of the other. Okay. Then it's going to be convenient to represent, we have basically the definition of the Markov perfect equilibrium exactly as before, but now the strategies depend on epsilon. Okay. It's very convenient for computation, okay, and for the estimation of the model to define Markov perfect equilibrium not in the space of actions, not in the space of these alpha strategies, okay, but in the space of conditional choice probabilities, okay? Then let's define in this context the conditional choice probability of player I as the probability that this player takes an action A conditional on the common knowledge information, okay? Now notice that these conditional choice probabilities, they play two different roles. They are the conditional choice probabilities from the point of view of the researcher, okay, as in single agent models, okay? This is what we observe, okay? The action of the players and the observable state variable X, okay? But they also play the role of the information that other players have about the behavior of player I, okay? Because the other players do not know the epsilon of player I, then from the point of view of a player, all what I know is probabilistically how player I will behave. Given that I know the common knowledge information X, what is the probability distribution of the actions of player I, okay? Then other players will have beliefs about what is the probability, the probabilistic behavior of player I, okay? Well, in this type of discrete choice models, Hodge-Miller inversion property also holds, okay? Under the independence of these epsilons across firms and over time, and the additive separability of this epsilon, okay? We have that we can obtain a one-to-one relationship between the choice probabilities and the conditional choice value function. And it's possible to show that that implies that there is a one-to-one relationship between the strategies in this space and the choice probabilities, okay? That is, if you give me a strategy function of a player, I can integrate it over the distribution of epsilon, and I obtain the choice probability. But if you give me the choice probabilities of a player, okay, I can use Hodge-Miller inversion to obtain value differences. And once I know value differences, I can construct the strategy function of a player, okay? Because I know that the optimal choice of alternative one if the value difference are lower or equal than some epsilon, okay, for alternative one, okay? Then I can always write in this model this strategy function in terms of inequalities, in terms of difference in epsilons and value differences, okay? And there is a one-to-one relationship between choice probabilities or a representation of strategies in the action space and a representation of strategies in the probability space. And there is no, under the additive separability of the epsilon and the conditional independence assumption, there is no loss of generality in representing strategies in this way or in this way, okay? Okay. Please. Please. Yeah. Excellent question. I should have been more explicit about this, okay? More explicitly, we are going to consider that we have exactly this structure, okay? I don't know if you can see it. This epsilon is additive, and there is one epsilon for each choice alternative, okay? Like in the single agent context, okay? Well, remember that you can choose, you can increase the quality of your product in 1 unit, in 2 units, in 3 units. You can reduce it in 1 unit, in 2 units. Then it's an investment decision, but it's a multinomial investment decision. It's not just whether to invest or not. Exactly, including a shock for no investment at all. Okay. Thank you. Very, very, very good clarifying. Okay, then give me the choice probabilities of the other players. Remember that with the strategies alpha, we have constructed basically what I call the indirect profit function player I, where I was conditioning on the actions or the strategy functions of the other players. And the same, I constructed the transition probability of the state variables from the point of view of player I by plugging in the transition probability, the strategy function of the other players. Well, we can do exactly the same now, but not plugging in the strategy functions, but plugging in the conditional choice probabilities of the other players, okay? And I can construct this indirect profit function from the point of view of player I by integrating the payoff function of player I over the distribution of the choices of the other players if these other players behave according to this with these choice probabilities Pj, okay? And similarly, I can construct this transition probability from the point of view of player I if the other firms behave according to these choice probabilities, okay? Like, I don't know how my competitors will behave because I don't know the epsilon of my competitors, but I know how probabilistically will behave. Taking that as given, I can construct an expected profit that depends only on my action and a transition probabilities of the state variables that depends only on my action because I'm integrating over the distribution of the actions of my competitor, okay? And given this, I can construct now again a Bellman equation, and I can construct an integrated Bellman equation, okay? Where basically what we are doing is integrating over the distribution of the epsilon, okay? Now, this value function is an integrated value function for player I if we integrate over the distribution of the epsilons of player I and conditional on the choice probabilities of the other player, okay? And this has this Emax expression, the maximum of this conditional choice value function and this epsilon integrated over the epsilon, okay? Where this conditional choice value function is just my expected profit of choosing alternative A today and my future expected profit of choosing alternative A today, taking into account basically that I believe that the state variables will evolve according to these transition rules where I have integrated the behavior of the other, okay? Okay, then we know that this is a single agent dynamic programming problem, okay? The combination of these two equations is a contraction mapping, and it's going to give us a unique value function, integrated value function, okay? Of course, this is the value function taking as given the choice probabilities of the other players, okay? what is the best response function of this problem? Well, we can represent the best response as a choice probability itself, okay? And we can represent the best response as in terms of the action of the player, okay? Is the optimal action, the optimal best response of player I, is just the R max of the conditional choice value functions and the epsilons. But then we can consider, okay, let's condition on X, and let's then integrate this over the distribution of epsilon, okay? And that gives me the best response of player I from a probabilistic point of view, okay? This best response of player I, this best response choice probability, is in fact, in equilibrium, the probability that the other players will use to predict the behavior of player I, okay? Then basically this defines a fixed point in the space of the choice probabilities of all the players. Give me the choice probabilities of players other than I will construct this expected profit, these transition probabilities. I solve a dynamic programming problem that gives me this conditional choice value function. And then basically you can think that these are logit probabilities. I will use the logit probability to construct this best response problem. I think that they have the logit, exactly, okay? This is a particular case where the epsilons are string value type, okay? Then basically this defines the Markov perfect equilibrium of this model in the space of choice probability, okay? For given probabilities of the competitors, I solve these single agent dynamic programming problems. I obtain this conditional choice value function. And then given this conditional choice value function, this expression gives us the best response in the probability space of player I, okay? In equilibrium, this should be self-fulfilling. And yeah, this vector of choice probabilities of player I should be the choice probabilities that the competitors use to predict the behavior of player I, okay? That's the nature of this, okay? Okay, then this is, well, you can see from here that the equilibrium existence is guaranteed, okay? Simply by Brouwer's fixed point theorem, okay? Basically, this mapping, everything is smooth here. For instance, in the logit case, this is a continuous function of the choice probabilities, okay? Then this function phi is a continuous mapping. These choice probabilities live in the simplex. Then by Brouwer's theorem, an equilibrium is. In general, yep, please. Exactly, yeah. Under the assumption of additive separability and conditional independence of these private information shocks, there is not any loss of information in terms of representing strategies as choice probabilities or representing strategies as basically functions in the action space, okay? And basically taking that into account, we can represent an equilibrium, a Markov perfect equilibrium, as a fixed point in the space of choice probabilities. And this is convenient for at least three reasons. First, we can see equilibrium exists trivially, okay? And second, most importantly, we are reducing, as we did in the case of single agent models, we are reducing substantially the dimension of the state space. We are getting rid of the epsilon, okay? And basically, before we have actions or strategies that depends on X and a vector of epsilons that are continuous variables as large as possible actions you can have. That's a huge dimension function, so strategy function. Here we have got rid completely of the epsilons, and now we have an equilibrium object that depends only on our probabilities that depends on it. And third, this brings basically our model much closer to our data, because these choice probabilities under some assumptions are empirical objects that we can estimate directly from the data, okay? Which is also what we have in the context of single agent models, okay? Why there are multiple equilibria? Well, good question. It depends on the nature of the problem. You can consider perhaps the most intuitive case are coordination games, okay? Models where there are positive strategic complementarities between the actions of the players, no? Then we can have an equilibrium. Suppose that we are in a model of adoption of new technologies, okay? And there are competition effects, but there are also spillover effects. If your competitors, other firms in the industry have adopted this technology, there are spillover effects, that knowledge spillover effect. You can learn from your competitors about the adoption of this technology, and that has good effects for your profits, okay? Then under that type of situation, we can have a situation equilibrium where if your competitor has not adopted, you will have very few benefits from this technology, and the best response for you is not to adopt, okay? While if your competitor has a high probability of adopting, you can get high benefit from this adoption, and your best response is to adopt, okay? Perhaps within this example, thinking in the adoption of a particular payment application, okay? An application, a person-to-person type of payment application where you can transfer money to your friends, okay? And we are considering a dynamic game of adopting this new technology. If nobody in your family or your peers or your friends has adopted this technology, they have very low probability of adoption, your best response is not to adopt. While if you are in the context of a situation where your peers have a high probability of adoption, your best response is to adopt. And we have this low probability of adoption equilibrium. Both are self-fulfilling, you can see, and a high equilibrium, okay? Well, of course, in any equilibrium, it should be self-fulfilling, okay? Please. Can you speak louder? Sorry. Excellent question. Identification and multiplicity of equilibria. Let me make a very strong claim here, okay? They are the opposite type of problems, okay? They are completely unrelated, okay? Multiplicity of equilibria means that given the structural parameters of our model, okay, our model have multiple predictions about the data, about the choice probabilities. And that means that we have a correspondence, not a function, but a correspondence from the space of structural parameters to the space of predictions or probability distributions of the data, okay? What is no identification? No identification is the opposite, okay? Is that the mapping that relates the data to our structural parameters, okay? That basically, given this data, which are the structural parameters that can generate this data, we have a correspondence if we have no identification. There are multiple structural parameters that can generate that same data, okay? And in one case, we have a correspondence that is multiple equilibria, is correspondence from the space of parameters to the space of predictions. No identification is correspondence from the space of predictions to the space of parameters, okay? You can have any possible combinations, but they are different type of problems, okay? And you have plenty of situations of models with multiplicity of equilibria where you have identification, okay? And we are going to see that in this type of model. Under some assumptions, basically the key assumption is that our model has multiplicity of equilibria, but suppose that in the data, only one equilibrium has been selected, okay? Under that assumption, we are going to be able to estimate consistently the choice probabilities. And given that we have consistent estimates of the choice probabilities, we are going to have the standard identification result in single agent models extends to dynamic games. We can go from choice probabilities to structural parameters, and the model is identical. The problem becomes more complicated, and now we enter, but notice that this is regardless of whether we have 1 equilibrium or 1,000 equilibrium, okay? We can go from the empirical choice probability to the model has multiplicity of equilibria, but we are assuming that in the data only one has been realized. If we have models with multiplicity of equilibria in the data, then now we start to have problems of identification. But this is not because multiplicity of equilibria in the data, because this is because we are introducing an unobservable variable that could be multiplicity of equilibria in the data or could be payoff relevant unobserved heterogeneity, that it's making difficult and sometimes impossible to identify non-parametrically the choice probabilities, okay? It's not because multiplicity of equilibria, it's because this type of unobserved, okay? And the two problems are very different type of problems, okay? More questions? Okay, sequential estimation, okay? Then typically in this model, we have several type of parameters, okay? Let me consider that the structural parameters, let me represent the structural parameters using theta. And we can distinguish 4 subvectors in theta. Let me use theta subindex pi to represent the parameters in the payoff function, okay? In the utility function, in the profit functions, okay? We have also structural parameters in the transition probabilities of the state variables. Let me call it theta f. We have the discount factors of the different players. Could be the same or could be different discount factor for different. And in principle, we could have also unobservables in the distribution of the unobservables, in the distribution of epsilon, okay? Then, under the conditional independence assumption, we can always identify the structural parameters in the transition probabilities of the state variables outside of the dynamic game, okay? Basically, we have data on xt plus 1, on xt, on at, on observable actions and observable decisions. We can construct, for instance, a likelihood function of this data to estimate the parameters in theta f, okay? Then the standard approach is to identify these structural parameters outside of the structural model, okay? Of the dynamic game or the dynamic structural, okay? It's also quite a standard to assume that we know the discount factor, because typically this is a structural parameter that is difficult to identify and typically is identified not with much precision unless we have some type of exclusion restriction that allow us to identify this. There is a very interesting literature on the identification of beta, but most empirical applications still assume that beta is known to them. Okay, and then we have the distribution of epsilon, okay, of the unobservables. As you know, the most standard assumption is that we have type 1 extreme value distribution. Then the only parameter to estimate there is a scale parameter, a sigma, that is the variance of the epsilon, which means that in general, what we are going to identify is the parameter in the scale in the payoff function up to some scale, basically divided by sigma. Okay, there are applications that consider nested logit structure, but let's focus then on the identification and estimation of pi of theta pi. That is the structural parameters in the payoff function. Okay. Then let me start with maximum likelihood estimation with a model that has unique equilibrium. In these models, it's possible to impose some, let me say, strong assumptions. that give us equilibrium uniqueness, okay? And then we can use, you are going to see, quite a standard nested fixed point out, okay? When we have equilibrium multiplicity of equilibria, still we can use, you are going to see multiple equilibria, yeah, you can see that we can use maximum likelihood, but this is going to be more complicated, okay? And then I will talk about sequential CCP map, okay? Now let me start with estimation under unique equilibrium, okay? Which are, in this type of models, which are sufficient conditions that have been used in some empirical applications to obtain equilibrium uniqueness, okay? Well, basically, two assumptions, okay? The first assumption is that the game has a finite horizon, okay? That is true in some empirical applications. We know that there is a finite horizon. In the typical empirical applications where this restriction has been imposed, that is not the case. There are, for instance, models of innovation and investment in research and development, where we know that these firms are competing for many years after our sample, okay? And we don't know for how many years, okay? Then it seems that it's more reasonable to consider that we have an infinite horizon model. Then we impose this finite horizon for convenience, okay? To have a model with equilibrium uniqueness. Now, finite horizon is not enough to have equilibrium uniqueness, okay? Then we need some additional restriction, okay? And the typical restriction that have been used in some papers is that within each period, these players make choices sequentially, okay? Then the simpler case, a model of market entry and exit, and we need to decide an order for how firms decide whether to be in the market or not to be in the market, okay? And then we say, for instance, okay, tenure in the market, how many periods firms have been in the market. The term is basically the sequence of choice. The firms that have been longer in the market choose first, okay? Then the combination of the two restrictions imply that we have a unique Markov perfect equilibrium, okay? And the intuition is very simple. Suppose that we go to the last period capital T, and we start with the decision of the player who decides the last one at period capital T, okay? Then for this player, it's a single agent decision problem. There is no multiplicity. Now we go within period capital T to the previous player. Now this player knows what the other players will do. There is a best response to the behavior of the last player, okay? Then this decision optimal response is also unique. And so on, we can go to the first player within capital T and is best respondent to the decision that he knows will make the other players after him, okay? And now we have in the last period in capital T a unique strategy functions, okay? And we can go now to period capital T minus one and use the same backward induction type of argument to show that the whole decisions are unique. There is a unique Markov perfect, okay? And that is in fact how these models are solved, okay? Using these basically single agent decisions kind of at every stage, okay? And unique ones, okay? Then that means that for a given value of the structural parameter theta, we have our model make unique predictions about which are the equilibrium choice probabilities of this player, okay? Then we have a well-defined likelihood function. The likelihood function, well, typically these models are estimated using multiple geographic markets. We are, in the case of empirical I/O, we apply these models to oligopoly markets. We have a few firms in the industry. We have a relatively short panel with a few periods. Then how do we get asymptotics? How do we get a good number of observations? Well, typically by considering that there are multiple geographic markets where these firms are competing, okay? And I have included here subindex M to represent these geographic markets, okay? And capital M is the number of geographic markets in our zone, okay? Then the likelihood function is the sum over markets of the contribution of market M, and the contribution of market M is basically the sum over firms, over players, and the sum over time of this probability. The part of the likelihood that depends on the choice probabilities and the part of the likelihood that depends on the transition. Typically, these are estimated in a first step, these parameters, and then we have a likelihood function that depends only on this. Okay, please. That's exactly true. Well, continuous time by itself does not give you equilibrium uniqueness, but the standard models of continuous time, the standard assumptions of continuous time that involves not only continuous time, but some particular assumption about when players can move. Basically, the key assumption, as you have described it, is that there is some Poisson process that determines when a player can play. And these Poisson processes are independent across players, okay? Then because there is probability 0 that two players can move at the same time, there is only one player making a decision. Of course, you could consider a continuous time model where there is a Markov Poisson process that determines that player 1 and 2 can play together, okay? And that might be more reasonable in some contexts, okay? Then it's not continuous time itself, but it's continuous time with together. The key assumption is that, and of course, you could do that also in discrete time. You can consider a model of discrete time. You say, well, suppose that we have high frequency data, and we can say, well, at every period, only one player has the opportunity to move, and that will give you equilibrium uniqueness. Yeah, you are complete. Yeah. Yeah. Excellent question, and this may matter a lot. Okay, what the papers do, the most applications using this type of approach has been Mitzi Igami's applications on models of innovation and investments in R&D. The standard approach to deal with that very important concern, because the order of move matters in dynamic games. There may be first mover advantage or first mover disadvantages, is to do sensitivity analysis. Okay, and definitely the predictions. I think that my view on this is that can be particularly important for counterfactual experiments. Okay. Because perhaps for the estimation of the structural parameters, the results on estimation of the structural parameters can be quite robust. And different papers show that the order of move doesn't play a very important role in the estimation of the structural parameter, in the values, the estimated values of the structural parameters. But now, once you go to the counterfactual experiment, this may have a very important implication. Okay? That's definitely that's why this approach is not at all the most common approach to estimate dynamic gains. Okay, there are important restrictions that, in principle, we would not like to impose in our day. Okay, but it's I think a good way to relate basically these type of models to the single agent models, because under the assumption of equilibrium uniqueness, or the restriction that give us equilibrium uniqueness, the estimation and the econometrics is not going to be so different to the single agent model. Okay, it's more convoluted because now we have to compute an equilibrium game, not just single agent decision, but other than that, basically is exactly the same type of econometrics. Okay. Okay, then basically we can use the nested fixed point algorithm. This is what this slide is about. Okay, then we have an outer algorithm that is maximizing the likelihood function, for instance, a BHH iteration. And at each iteration K, we update the vector of the structural parameters by calculating the score of the likelihood function and calculating this outer product of the score, the inverse, multiplied by the gradient of the likelihood function, and that is going to give us a new value of theta. Okay. to obtain these scores, okay, we know that these scores are the derivatives of this likelihood, or the derivative of these choice probabilities with respect to theta, which means that we need to calculate the equilibrium choice probabilities, okay? Then at each iteration of this nested fixed point algorithm, at each outer iteration, we need to calculate a new equilibrium of the game, calculate the gradient to calculate these scores, okay? But basically, conceptually, the same as the nested fixed point algorithm in single agent. Huh? What if we have multiplicity of equilibrium? Okay. Then in this class of models, a paper by Doroselsky and Satterwhite in Theoretical Economics shows that though there is multiplicity, there may be multiplicity of equilibria. The number of equilibria is generically finite. There is a finite number of equilibria. For every value of theta, the model may have multiple equilibria, multiple Markov perfect equilibria, but there is a finite number of these equilibria. Okay? Then let me use tau to index this equilibrium. Okay? Then in principle, one could think, well, now we do not have a model that generates unique predictions. Okay? For a given value of theta, we have a correspondence because we have multiple choice probabilities. That means that we have a likelihood correspondence, not a likelihood function. How do we maximize a likelihood correspondence? That's not well defined, okay? That's not a known estimator, okay? And how can we, the first reaction will be maximum likelihood is not well defined with multiplicity of equilibrium, okay? But that's not the case. We can extend the concept of maximum likelihood estimation to models with multiplicity of equilibria by introducing basically incidental parameters that basically is which equilibrium has been selected, okay? Then let's consider now a likelihood function where it's not only theta the vector of structural parameters, but tau is also a parameter that we want to estimate. We want to estimate which are the structural parameters and which equilibrium has been selected, okay? Then that is this likelihood function here, okay, or log likelihood function. The sum over the sample of the log probabilities where we have here the theta, but we have also here the index of which equilibrium has been selected, okay? And we want to identify not only theta, but also which equilibrium has been selected, please. Excellent question. We are going to get there. But given that today Bob is not in the audience, let me say that because Hodge-Miller CCP estimation in the context of this type of games is going to work terribly, okay? Because we have a very large state space, okay? And basically think that we have 10 firms, 10 airlines competing in a market where they have decided which routes to operate, okay? Model of market entry and exit with 10 airlines, okay? Very standard, okay, in the airline industry. And each of these firms have 4 or 5 state variables. The state space for each firm is basically 1,000. But then we have 1,000 to the power 10, okay? Then we have a huge state space, okay? The non-parametric estimates or even the semi-parametric estimates of these choice probabilities will be super imprecise, okay? and basically garbage in, garbage out, okay? If you use any two-step semi-parametric estimation where the initial non-parametric estimates are very imprecise, you are going to get estimates of the structural parameters that are not only imprecise in terms of high variance, but very imprecise in terms of very large finite sample bias, okay? Then this can be consistent, and in fact, root and consistent, but in terms of finite sample properties, precision, they are super good. And there are multiple Monte Carlo experiments that have shown this, okay? And this is well known in the two-step semi-parametric literature, okay? Of course, you could think in improvements of refinements of this CCP estimation, and you could consider double debiasing methods and this type of things. And this is a very interesting type of literature to explore. There will be a limit at the end of how much you can improve this non-parametric estimation of the conditional choice. Okay. But yes, we are definitely, there is huge computational cost here. Okay, there are trade-offs. Okay, here the cost is huge computational cost in terms of repeated solution of this Markov perfect equilibrium. At the end, we are going to get, if this is doable, okay, given the dimension of the state space, we will get very precise, hopefully very precise estimate of the structure. Okay. Okay, then excellent question. Okay. Then this is a well-defined maximum likelihood estimator. Okay. With all the good properties of maximum likelihood estimation. Okay. Notice that there is an implicit assumption in the definition of this maximum likelihood estimation. Okay, is that we are considering just a single tau for all the markets and all the periods. Okay, then we are saying that there is only, in all our data, there is only one equilibrium selected. Okay. Okay. We could relax this, okay, to a certain extent. You could, if we have multiple geographic markets, we could say, okay, we are going to consider markets in the east, in the west, in the north, in the south. We are going to consider different groups of markets according to some characteristics, and we are going to allow tau to be different across different markets, because perhaps for some reason, different markets have selected different type of equilibrium, okay? And we can extend this, trivially, this maximum likelihood estimator to allow for this tau to vary according to some characteristics of the market. Can we do it by allowing tau to be completely different across different markets? No. In that case, we get, okay, if tau has a subindex M and every market M can have selected a different type of equilibrium, this estimator will be inconsistent, because we will be in the context of the incidental parameters problem, okay? We have that the estimation of this market selection, we are estimating basically each tau with very few observations. This estimation is inconsistent, and this inconsistency of tau will translate into inconsistency of the parameters. Okay? But under this assumption that basically we can restrict how basically multiplicity of equilibria in the data, we can deal with multiplicity of equilibria in the model, okay? We have a model with multiple predictions. We have a model that gives us correspondence. Is that a problem for maximum likelihood estimation? Not at all, okay? Okay. Once we introduce this subindex, this multiplicity of equilibria, the nested fixed point algorithm becomes a little bit more convoluted, because we need to maximize with respect to theta, but also with respect to tau, okay? The perhaps obviously more serious problem is that now for every value of theta of the structural parameters, we need to get all these guys, okay? then we need an algorithm that give us all the equilibria that the model has. Obtaining one Markov perfect equilibrium can be challenging when the state space is large. Obtaining all the equilibria that the model has can be very challenging for most dynamic games. Tomorrow, Bertel and Fedor will tell us about some particular type of dynamic games with a very nice structure where that is going to be very feasible and computationally quite efficient. They will give us a very efficient algorithm to obtain all the Markov perfect equilibria, and therefore basically to implement a maximum likelihood, to make maximum likelihood estimation in this context feasible. In other type, more general type of dynamic games, this is super challenging. And that's why for general type of dynamic games, nobody has used this maximum likelihood estimation. Okay? This is a well-defined estimator with all the good properties of maximum likelihood estimation, but very challenging to implement. Okay? Okay, then let me going to, it's a way of introducing the sequential estimation and the two-step estimation. Let me now define a different type of likelihood function that we could call it pseudo likelihood function or quasi likelihood function or extended likelihood function. You are going to find in the literature this likelihood function denoted in the three ways: pseudo, quasi, or extended. Okay, and basically, instead of equilibrium probabilities, what we are considering here is a model. Consider a model, our model, where now we take players' beliefs about the behavior of other players as parameters to estimate. Okay, and we have a dynamic game, but suppose that we say, okay, suppose that we for the moment abstract from equilibrium and say, in principle, firms can have any beliefs, okay, about the behavior of the competitors, okay? Then they can have any beliefs about the choice probabilities that the competitors will use to make their investment decisions, okay? Then under that type of model, the choice probabilities of the competitors, the vector of choice probabilities for every competitor and for every state is a very large vector that I denote as P, that now is part of the parameters of the model, okay? Is the beliefs, let's treat it as the belief that players have about how the other firms will behave, okay? And if we treat these as parameters, then now the probabilities that our model predicts, they are not equilibrium probabilities. They are best responses to the beliefs that player I has about the behavior of other players, okay? And we have seen that if we take as given the beliefs that a player has about the strategies of the other players, we have a single agent dynamic programming problem, and we have well-defined functions, best response functions, not correspondence, okay? Then these best response probabilities will be basically the logic probabilities that I have presented before, where we take as given the choice probabilities of the competitor, okay? And standard logic probabilities here, okay? And we have a likelihood function, okay? Now, of course, you can see that the problem is that now we have a huge space of parameters, okay? Theta can contain a few 10, 20 parameters, okay? But P will contain millions, potentially millions of parameters in many applications, okay? Then, in principle, you could define, okay, let's define the maximum likelihood estimator of theta P as the values of theta and P that maximizes this likelihood function that depends on theta and beliefs. But we will not get identification, okay? There are multiple, infinitely many combinations of theta and beliefs that can rationalize the behavior of them. Without restrictions, we cannot identify separately preferences and beliefs, which is a very common result in economics, okay? Okay, then one possibility it will be to say, okay, then let's consider a definition of the maximum likelihood estimator as a constrained maximum likelihood estimator. Okay, now it's not P cannot be anything. Okay, we are maximizing this pseudo likelihood function, but under the constraint that beliefs are self-fulfilling, beliefs are in equilibrium. This vector of beliefs P are the actual choice probabilities. Okay, every player is best responding to the choice probabilities, to the actual choice probabilities of the competitor. And that's what this restriction means, okay? That we are imposing the restriction that choice probabilities are in equilibrium. Then you can see that, and this is a definition, an alternative definition of the maximum likelihood estimate. It's a constraint estimator, it's a constrained maximum likelihood estimator, where basically these incidental parameters that are beliefs should be equilibrium beliefs, okay? And then we can define a Lagrange function and define this maximum likelihood estimator as the maximizer of this Lagrange function, okay? And this is the approach in MPEG to estimate dynamic gains, okay? Is to find this vector that basically solve the Lagrange function. Well, again, this is computationally very intensive, okay? One of the main causes of implementing this estimator is calculating basically this Jacobian matrix, the Jacobian of the best response function with respect to the choice probabilities of the competitor. This is a huge object. You can think that choice probabilities, we can have millions of choice probabilities. This is a square matrix with the same dimension as the state space, okay? And basically we need to, for each dynamic programming problem of each player, we need to perturb basically the choice probabilities of an agent in a particular state to see what will be the effect of that perturbation in one single probability on the vector of choice probabilities of a player at every possible state. And we don't have, of course, any closed form expression of any kind of thing. And we need to recompute this Jacobian matrix at each stage in the implementation of this estimate. Okay, then this is computationally very. Okay. Okay. Then let's go to sequential or CCP methods to estimate this type of model. Okay. Then let me be a little bit more specific or restrictive in the specification of the model, is because it's under this additional restriction where CCP method will be more computationally efficient. Okay. Then let's suppose that the payoff function of a player is multiplicative. It has a multiplicative structure in the structural parameters. Okay. Basically, all the structural parameters appear basically as slope parameters in the payoff function of the player. Okay. Then this is the structure of the conditional choice value function of a player. Is basically the expected value of all the future payoff given that this player chooses action A and we are in a state. Okay. The good thing is that we can write this left-hand side as function of choice probabilities and transition probabilities. Okay. And it's possible to show that the conditional choice probability of conditional choice value function of player I, taken as given the choice probabilities of all the players, can be written basically in this index form, okay? Where H is just the present value of the future values of H given this choice and a state at period T. And this E tilde is basically the expected value of future epsilons, taking into account that the future epsilon that will be realized in the future are the epsilons associated with the optimal choices. Then we have a selection of the optimal epsilon. And the expected value of the optimal epsilon, okay, has in the logic model has this very simple structure where gamma is the Euler constant, and this is the logarithm of the choice. Okay? Then this, if we know beta, of course, we know this, the functional form of our utility function. We can estimate choice probabilities in a first state. Then we can construct these objects, okay? We can construct this object by using a solution of a system of linear equations, as I mentioned the other day, or we can construct this object just by simple forward simulation, like Hodge, Miller, Sanders, and Smith, or Bayari, Benkar, and Levy, okay? Then once we have estimated the choice probabilities of the data, these basically become known objects, okay? And then we can, then our pseudo likelihood function is a likelihood function where the best response probabilities are the best response probabilities to the probabilities that we have estimated in the data, okay? Then this is data in the denominator as well. And basically what we have here is just the structure of a multinomial logic model, okay? And therefore the two-step estimator is just, in the second step, is a standard multinomial logic type of estimate, okay? Okay. Then this estimator is consistent, asymptotically normal. Let me say, what is the main challenge of this estimator? The main challenge is estimating the choice probabilities in the first step, okay? We have a large dimensional state space, okay? And typically these choice probabilities are going to be estimated with very little precision, okay? Which is going to introduce bias and imprecision in the estimates of these objects, and that is going to translate into imprecise estimation of the theta parameter, okay? Then computationally is very simple because you can see that in terms of computational cost is basically we need to calculate only once basically these objects, okay? No solution of any dynamic programming problem, no solution of any equilibrium, Markov perfect equilibrium, just this calculating these valuation operators only once, okay? Which reduces very much the computational cost of estimating the parameters, okay? Now, Monte Carlo experiments have shown that these, when the dimension of the state space is large, these parameter estimates can be very imprecise, okay? Then one possible approach that I have proposed in my papers with Pedro Mira is to consider the so-called nested pseudo-likelihood estimate. That is in the spirit of the two-state estimator, but it's a full solution method. At the end, we are going to get estimates of the structural parameters that solve the dynamic game, that are an equilibrium of the dynamic game, okay? When the estimator is defined as, okay, the estimator, the NPL estimator is defined in terms of two conditions, okay? This is a pair of structural parameters and choice probabilities that solves two conditions. Given the vector of choice probabilities, we have that theta maximizes the pseudo likelihood, okay? Then given this P, okay, we can construct this, we can construct this H tilde and E tilde and construct a multinomial logic likelihood function and obtain theta that maximizes the likelihood of this multinomial logic, okay? Very simple, okay? The other condition is that given theta, this vector of phis is an equilibrium, okay? Then you can compare these two conditions with the conditions for maximum likelihood estimation. Remember that these were the conditions for maximum likelihood estimation. Then they are related, but they are different. Basically, for maximum likelihood estimation, we still have that given theta, P should be an equilibrium. That's the first condition. But basically, we are avoiding completely this condition for the MPL estimator. That is, the derivative of the likelihood with respect to the choice probability is equals to 0. This is this condition that implies this huge Jacobian matrix is not a condition that defines the MPL estimator. Okay? It's possible to show that for single agent dynamic programming models, it doesn't matter because these models satisfy the so-called zero Jacobian matrix, which means that for single agent models, this is equals to 0. Okay? And therefore, we don't need to impose this restriction. Okay? And then the MPL estimator in that way is a computationally efficient way of calculating the maximum likelihood estimate. Okay? In the case of dynamic games, this comes with a loss of efficiency. We are going to get consistent estimators that do not impose this restriction. But that is exactly what we want to avoid. We don't want to calculate this large Jacobian matrix. Okay? Then the algorithm to obtain this MPL estimator is a very simple extension of the two-step CCP estimator. In the two-step CCP estimator or Hodge-Miller estimator, we estimate non-parametrically the choice probabilities. We construct this H tilde and E tilde. We define this multinomial logit likelihood function and obtain theta as the maximum likelihood estimator of this multinomial logit. And that's it. That's the two stage. Okay? The MPL estimator basically is based on the intuition. Well, now that we have got a maximum likelihood estimator or an estimator, a consistent estimator of theta, as a byproduct of this estimator, we have choice probabilities that are parametric choice probabilities. Okay? Once we have estimated theta, now we have this logit expression that give us estimates of the choice probabilities according to this expression that we expect to be substantially more precise than our original non-parametric estimates. Okay? Then why not taking now this estimate of the choice probabilities, okay, to do the same exercise again? Okay? Let's take this estimate of the choice probabilities. Let's construct new estimates of H, new valuation of H tilde and E tilde, and do the same exercise again. Because we are using more precise estimate of the choice probabilities because they are imposing all these restrictions associated with the multinomial logit model and this index model for the utilities. Our choice probabilities in the second step should be more precise than in the first step, and that should translate in more precise estimate of the structural. Okay? And you could do this a limited number of steps, okay? Or you could do this up to convergence. If you do this a finite number of steps, basically you can see this as a procedure to improve basically the finite sample properties of the two-step estimate, okay? If you do this up to convergence, this is basically, you are going to get this MPL estimator that basically satisfies the equilibrium condition, okay? That imposes exactly equilibrium. But you can see that at each iteration, we are not solving any dynamic, any Markov perfect equilibrium. Basically, we are just using choice probabilities, new choice probabilities to calculate new valuation of H tilde, E tilde, which is computationally much simpler than obtaining basically the maximum likelihood, that's solving the equilibrium. Okay? I'm sorry for going over time. Okay, let me stop it. Okay.